Hi, and welcome to this quick review of carboxylic acids and esters. So we'll start with the synthesis of carboxylic acids and then move on to their properties and some of its reactions leading to esterification and perhaps even the mention of acid anhydrides as well. We won't go into all the derivatives of carboxylic acids because that can be covered in a separate clip. So although in actual fact there's quite a few different ways of making a carboxylic acid that are available to your average organic chemist, the most familiar to most A-level students would be the full oxidation of a primary alcohol or an aldehyde. So the O in square brackets means an oxygen atom provided by an oxidizing agent, and obviously the most commonly used one that's referred to in A-level chemistry is potassium dichromate acidified with sulfuric acid. So the carboxylic acid group is written in structural form as COOH. So thinking about the properties of carboxylic acids, so because the OH bond is polar, this makes it soluble in water due to hydrogen bonding, because all three of the criteria for hydrogen bonding are in place. Obviously, if you've got hydrogen bonding, as well as the background London forces, you'll have a higher boiling point because it has more energy requirement needed to overcome the hydrogen bonds. And they also behave as weak acids, so they partially dissociate to give H+ ions or protons in aqueous solution. So the reactions of carboxylic acids can be broken down into redox reactions or acid-base neutralizations. So looking at an example of a redox reaction, you have the acid reacting with a metal to make a carboxylate salt and hydrogen gas. So it's obviously a redox reaction if you check the oxidation numbers of the relevant atoms. So you can see that calcium is oxidized and hydrogen is reduced. And a good tip at this point is to watch out for balancing errors. Always check the charge on your metal ion, because the carboxylate ion is always -1 or -1. So therefore, if you use calcium, it's going to be 2+, so therefore there are 2 carboxylates. So as you'd expect, acid-base neutralizations can involve alkalis, metal oxides or carbonates. If you think back to your first year, you'll remember that all three of these can behave as bases. So if we look at it from the point of view of a Venn diagram, you can see that alkalis are a subset of bases, and that all of the species that are in pink can accept H+ from an acid. So here's a little exercise for you to do. You'll need to pause the clip to give it a go. If we take these three bases in their solid form, aluminium hydroxide, rubidium oxide and strontium carbonate, what I'd like you to have a go at is predicting the equation for when each of these are added to ethanoic acid, and I'd like you to name the carboxylate salt. So there's some naming and there's some equation predicting to do as well. So pause the clip and give this a shot. So those are the three equations taking into account the stoichiometry that we're talking about, the mole ratios. Very important to remember that. And the names are aluminium ethanoate, rubidium ethanoate and strontium ethanoate. So now let's turn our attention to some other reactions of carboxylic acids. And what these reactions will focus on is carboxylic acid derivatives. So we'll start off by looking at esters because they're quite an important part of the A-level syllabus. So first of all, esterification is the synthesis of an ester using an alcohol and a carboxylic acid. So as you can see from the diagram, water is removed, and because this is quite a difficult process, involves breaking quite a lot of bonds, the presence of concentrated sulfuric acid under reflux conditions is needed for this to actually work. So when you write out an equation for esterification, if they want the reaction conditions, you'll need to put down concentrated H2SO4 and reflux. So in reality this reaction is actually in equilibrium, but the reflux conditions plus the presence of H2SO4 shift the position of equilibrium significantly to the right, so we treat it as a forward reaction, in other words. So if we look at the structure of the ester group, you can see that there's two R groups. I've actually given them slightly different setups. One is R and the other one is R with an apostrophe. Excuse me, my voice is going a bit. So the R apostrophe was originally the alcohol as ROH, but R was originally the carboxylic acid as RCOOH. So this is how we derive the naming. So esters have names that come in two parts. The first word ends in "-ile", the second word ends in "-OH". So in the little diagram at the bottom you've got ethyl propanoate, you've got propyl methanoate, you've got methyl butanoate, and you've got propyl ethanoate. So here's an exercise to try. Pause the clip and predict which alcohol or acid combination gave rise to each ester, and then write an equation for each one's formation. And play the clip again when you're finished so you can check. So we've got the two combinations, or the four combinations I should say, of alcohol and carboxylic acid. Now what we'll do is put the equations up so you can check those as well. So there are the equations for you, and just to remind you, the YL part of the name "-ile" comes from the alcohol, so as in methyl, comes from methanol. The OH part comes from the carboxylic acid. And just to illustrate it, I've labelled the four esters that we made with those combinations on the left hand side. So we've got ethyl propanoate, propyl methanoate, methyl butanoate, and propyl ethanoate. So it's worth at this point maybe pausing and going and trying some practice examples before we go on, because it just gets your head around it and it makes you comfortable with the whole idea, and it means it doesn't slow you down in an exam. It's what we're trying to get you to do, isn't it? Just to be a bit more confident in doing exam style questions. So when you've done a few, we can continue and start looking at some of the other reactions of esters. So there's an alternative esterification method using a type of compound called an acid anhydride. And the acid anhydride group looks something like this. So the R groups can be the same, in which case two of the same carboxylic acid molecules had a water molecule removed between them. So if we were to take butanoic anhydride, for example, remembering that R will be a propyl group, so that the carbon that's on the C double bond O adds on to that to make it butanoic anhydride. And if we look at the equation for the production of butanoic anhydride, you can see it's 2 moles of butanoic acid giving you 1 mole of butanoic anhydride and also 1 mole of water. So here's a little exercise for you. Using this new acid anhydride, where I've replaced one of the propyl groups with an ethyl group, try and predict the structure and the name of this acid anhydride, and also write out the equation for its formation from 2 moles of carboxylic acid. So pause the clip, have a go, and then resume playing the clip when you put something down so you can check how you've done. Okay, so hopefully you got something like that. And now what we need to have a look at is how we can use these types of compounds to make esters. So because acid anhydrides are so reactive, they don't require the concentrated sulfuric acid or reflux conditions to esterify that an alcohol and a carboxylic acid combination might do. So let's now have a look at ester hydrolysis. So in the presence of an alkali such as sodium hydroxide and under reflux, what happens is the ester is converted to a carboxylate salt of the alkali. So the carboxylate salt will be based on the carboxylic acid that the ester came from. So in this case on the diagram you can see it came from propanoic acid, so we get sodium propanoate. The original alcohol was ethanol, and we get that back. However, if we do the same thing but in the presence of a dilute aqueous acid, the water in the solution hydrolyzes the ester and the dilute acid acts as a catalyst. And you can probably spot that this is actually the reverse of the esterification we talked about a few minutes ago. So let's finish off with a look at some of the uses of esters. We've got solvents. An example might be ethyl ethanoate used in nail polish remover. We've got octyl ethanoate, for example, being responsible for the flavour of oranges. And phenyl benzoate is a perfume that's found in many bathroom products. So if you have a look on the labels of perfumes and shampoos and things like that, you'll definitely find it there. So this brings us to our end of the review on carboxylic acids and esters. Hopefully you found it a useful introduction, or if you're reviewing it after doing it already, it's been useful revision. So for now, thanks for listening, and see you soon.